Welcome to the video about the binomial theorem. In this video, we're going to learn how to raise any binomial to an integer exponent. So how do we do that? Well, let's start with a binomial. Our binomial here is x plus y, and we are raising it to the nth power. Right? This is just a general binomial raised to some exponent. So that means what we're writing down here is the actual theorem. We are going to write down what this would result in if we were to expand it out by multiplying. We're just going to skip the multiplying part. To do that, we will start the first term of our polynomial with a combination. So hopefully you've already watched or learned about combinations. So here we're going to use the same exponent, right, as the binomial has, as the number of things we're choosing from, and we're going to choose 0. In other words, we're going to go to the nth row of Pascal's triangle and take the 0th term in that row. All right, so that's going to start things out. We're then going to multiply that by whatever the first term of the binomial is, in this case x, and we're going to raise that x to n, whatever our original exponent is. The other thing we're going to do is then multiply that with the second part of the binomial, in this case y, to the 0 power. And just to point out a few things, notice that the exponent on the y matches the number here that we're choosing. Okay, that's going to happen on our next term as well, right? We're now going to write the second term of that polynomial. We're still going to choose from n things, right? But this time we're choosing one of them. See how the y's exponent matches the number of things we're choosing. But what has changed is that the exponent on the x has now decreased by 1. So what's going to happen, we have a bunch of patterns we could see here. We see that the exponent starts out being as high as it possibly can, right? The original exponent. It will decrease by 1, whereas the exponent on the y is going to start out as low as it can, 0, and increase by 1. So that next term, now we're choosing two things for our combination. That exponent on x has decreased by 1 again. The exponent on y has increased on 1. We would continue doing that as long as we needed to do that, right? Because we're not sure if we're squaring, cubing, raising to the 4th power, whatever it is. Right, so we're not sure how many terms this is going to have in between here. We do know that we're going to eventually stop once we get to n choose n. The exponent on x will be 0, and the exponent on y will be back to this original exponent here. All right, so this is not a formula that you memorize in this format. You memorize the ideas behind the formula, right? And those ideas are that we're using a row of Pascal's triangle based on this exponent. So we are decreasing the exponent on the first term and increasing the exponent on the second term. Our first example, we have x plus 2 to the 4th. So notice we're still keeping that first term here, x, so we're not going to be doing a whole lot different than the actual formula up here, but we do have a 2 instead of a y, and now we have an exponent that's an integer, right? So we will know what to put in our combination now. So let's start off our combinations. We know that the first one's going to be 4 choose 0, next one's 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Notice that I did all of my combinations first. Not everyone does that. It's just something that I like to do. I like to write the things in the order that the pattern follows so that I don't forget my place in the pattern. Otherwise, I'd be doing 3 different patterns simultaneously. I think that is more confusing, but it's totally fine, right? People do it. I like to work with the x term next. So I'm going to start that off with x to the 4th. And that's the one that's going to decrease every time. So now I have x cubed, x squared, x to the 1st, and x to the 0. And the last part, we work with the second term of the binomial, so in this case 2. That's going to start out with an exponent of 0 and work its way up. So 0, 1, 2, 3, right? So however you want to get to this, that's fine. That's just a way that I do it. It helps me keep organized in my brain. Okay, so from here, we now need to do the simplifying. So my suggestion is that you go to Pascal's triangle and you look for row 4 and you get these 5 values from that. So you get 1, 4, 6, 4, and 1. Next part, we're going to simplify with exponents. So in here, we get x to the 4th, but 2 to the 0 is just 1, right? So that doesn't change anything. We don't need that. On the second part, we get x cubed, and 2 to the 1st is 2. So we still have some multiplying that needs to happen in there. Next one, we get x squared times 4. Next one is x times 8. And then on the last one, x to the 0 is going to disappear because that's just 1. And then 2 to the 4th is 16. So we are so close to being done. We just need to do a little cleaning up here, right? Some multiplying between the 4 and the 2, between the 6 and the 4 and the 8. Obviously 16 and 1 is 16. That cleans up real nice. And notice that a binomial raised to the 4th power has 5 terms, okay? When we talked about Pascal's triangle in the previous video, I mentioned that things like row 8 have 8 numbers in them, but that's if you call the beginning thing the 0th term. We don't call this first term of a polynomial the 0th term, right? It was just advantageous to us to call that the 0th term because it matched up with these combinations, the pattern that was happening in there. So that is what we would get for our answer without doing any giant multiplying problems. Obviously, we still did some multiplying here, but I would much rather just be doing this simplifying work than doing x plus 2 times x plus 2, take your answer, multiply by x plus 2. Take your answer, multiply by x plus 2, right? Super annoying. So let's do one more example. I just wanted to go through what happens when we have a negative in here. That's one reason I picked this example. But I also changed it up so we don't just have x and y's, right? We have other coefficients in there as well. Okay, so here we go. We are raising a binomial to the 5th power. So I would get my combinations from the 5th row of Pascal's triangle. It's hard to fit these all on one line. If you can't fit it all on one line, please don't worry about that. I'm just trying my best to do that. All right, next part, we take this first term, in this case 2 to the a. Don't forget to wrap it into parentheses, right, because we're raising it to an exponent. That's going to go to the 5th and going to go down from here, so to the 4th, to the 3rd, squared, to the 1st. I'm not even going to write it over here because I know that this is going to be 2a to the 0, which just disappears to 1, right? I'm going to save some room there. Next part, we're going to start with negative 3b, right? Negative 3b to the 0 power. But to the 0 power, that's just going to disappear. That's 1. On this one, we have negative 3b to the 1st. This is negative 3b squared, negative 3b cubed, negative 3b to the 4th. I'm going to do it. I'm going to make it negative 3b to the 5th. Just squeezed it in. Okay, so the other thing you could do is if you don't want to bother writing down the combination notation, you could just go to the triangle, right, and get those. So that's what I'm about to do right now. I'm about to go to my triangle. And if you didn't have a triangle available, you could always make one starting from the beginning, right? If you just wanted to do it recursively, or you could calculate each of these combinations out. I just don't think that's the best use of my time right now. If I already have a triangle available to me, I'm just going to copy these down. We get 1, 5, 10, 10, 5, and 1. All right, now we have to do some exponent stuff here. So 2a to the 5th is 32a to the 5th. That was gone. 2a to the 4th is 16a to the 4th, but we still have a negative 3b to multiply by. 2a cubed is 8a cubed. Here we have to square the negative 3b. Okay, that's going to turn into a positive 9b squared. 2a squared is 4a squared. Negative 3 cubed is going to stay negative, so negative 27b cubed. Here we just have a 2a. Negative 3 to the 4th, that's going to go to positive 81b to the 4th. Oh, here we go. And now here we have negative 3 to the 5th. I'm just going to use my calculator to make sure that I am doing that correctly. 3 to the 5th power is 243, but it's negative. Oops, so we want negative. Here we go, 243b to the 5th. Okay. Now it's time to do multiplying, right? We were doing the exponents. Now we have to actually multiply these terms together. So you definitely want to keep a calculator handy. First term's pretty easy though. We get 32, a to the 5th. All right, on this one, I'm doing 5 times 16 times negative 3, and I get negative 240. Don't forget our variables here, a to the 4th, b. Next one, we're going to get positive, right? So 10 times 8 times 9, that should be 720. And our variables are a cubed, b squared. Next one, we're going to get a negative number, right? 10 times 4 times negative 27. What is 40 times 27? Negative 1080. A squared, b cubed. Next one, we're back to being positive. 2 and 5 multiplied to 10 times 81 is 810. A, b to the 4th. And this one's already done for us, negative 243, b to the 5th. Now that might feel like a lot of work. I mean, it is, right? But it's much less work than actually doing the multiplying out, which is crazy when you think about it, right? That this is the shortcut. But the binomial theorem is a very nice shortcut to have, especially if you just wanted to get to a certain term in here, right? We were doing the whole thing, but if you just wanted to get one of those parts for some reason, you would be able to do that. So notice what happened when we had the negative here in the binomial. Our terms are now alternating signs, right? They're going back and forth between negatives and positives. All right, the other thing I wanted to point out is that when we raise it to the 5th power, we should have one more than that terms. 1, 2, 3, 4, 5, 6. Perfect. That is all for this example. I hope that you find that useful and saves you some time.